Right, brilliant. Well, I hope you enjoyed a fine northern lunch, and we'll start off our next session. Hopefully we'll have some really interesting talks about a range of skills and different training opportunities on offer. But we'll start first with Neil Dickens, talking about startups.
Thank you. Right, tell them what you're going to say it, and tell them what you just said. So what I'm going to say is, if you're an angel investor, get in touch with me. If you know an angel investor, get in touch with me. Right, that's what I'm going to tell you later. So, no presentation, but I have a prop. Now, my prop's going to come out about a quarter of the way into this talk, so after that, you're sort of on your own. I'm sorry, no more exciting stuff. But at that point, that'll be quite good. That'll be quite exciting. So, Neil Dickens, the founder of IC Resources, which is what I believe the biggest semiconductor recruitment company by turnover in the world, definitely Europe. So I started the company 25 years ago. The first week, myself and my business partner realized that the sort of standard recruitment model of working with a customer, as an individual working with a customer, didn't really make sense. Because if one day they need a digital chip designer and the next day they need a power electronics engineer, then I'm not sort of optimized to deal with those two. So he did analog IC design, I did digital IC design. And we've rolled that model out to 65 recruiters who each specialize in a different sector of what I would call the deep tech market. So even though on the semiconductor side, out of those 65 people, about 25 to 30 specialize in semiconductors only. That's why we have the biggest turnover. But the rest do electronics, software, operations, and sales and marketing. For our European clients, we have sales and marketing activities in Asia and the US as well, so that because they want to grow internationally, we're then their recruitment partner. So essentially, other than accounts and legal, we are your recruitment partner. An example, Cambridge Silicon Radio. We started working with them the first year they started, because that was the first year we started. We placed 450 people with them before they were acquired by Qualcomm for $2.5 billion. So that's an example of how we work with companies. So, but I'm not here to talk about that. I'm here to talk about three other things. So the first one is that I am extremely optimistic about the UK semiconductors and deep tech world and future, for the reason I mentioned earlier about the opportunities that I believe are on offer to all of us at the moment. Also very positive about the government interventions. The world is jealous of our SEIS and EIS program, which I'll talk about later. The R&D tax credits are great. Innovate UK, though a big organization, and therefore naturally any big organization has certain issues, but actually Innovate UK is a fantastic organization as a whole. So, all of government is supporting us. Everyone seems to be moving in the right direction, with the exception of the enemy in the room. The enemy in the room is the Home Office. And this is where the prop comes out. So, a couple of back of the envelope calculations. So, the Home Office has decided that hiring anyone from other than our own shores should be one of the most difficult and expensive things you can do as either a startup or a large company. So while the rest of the world is encouraging, in fact, grabbing people with lassos and pulling them into their countries, the Home Office only is doing its absolute best to put a middle finger up to us in our industry and anybody outside of our shores. What do I mean by that? The cost of a startup hiring two individuals, let's say engineers, and two dependents. So let's say one of those individuals is single and one of them has a husband and a daughter, right? The cost of that in Germany for a 5-year work permit is £400. Germany has a blue card scheme. So if you qualify for a work permit, and you don't need a license. You don't have, basically, if your job qualifies for a work permit, the German government charges you 100 euros for the work permit, and after 3 years, they charge you 100 euros for a renewal, right? So 2 people, 400 euros, 350 quid, whatever. Holland, it would probably cost you about 8,000 euros, 10,000 euros, because they charge you for your permit to start, and then they do an annual check, and they charge you for the annual check. France, probably about 5,000 pounds. Most of that is the legal fees, just to make absolutely, because it's relatively complicated in France, so to make sure that that happens, you have to pay a lawyer to basically get your application through. UK, 28,000 pounds. 400 pounds in Germany, 28,000 pounds in the UK. Here is why. Okay, yeah, where's the top of my list? Okay, so, yeah, 2,800 quid in legal costs to get your license to be a company that can bring people on. Takes 3 months, by the way. And 500 quid for that license. So that's then there is a fee or a license for every person you hire. So that's another 240 quid times 2, and then a 3,000 pound legal fee to process that application, because that application is unbelievably complicated. If you try and do it yourself, you will probably end up using one of those lassos I mentioned on yourself in about 2 months later. And then another 1,300 quid in legal fees to manage the process of getting those dependents also into the country. An immigration skills surcharge. So you've had to pay for your license, but then for every person you hire, you pay an extra fee. Well, hey, that's a good idea. Let's generate some more cash. 364 pounds times 2. Then there is the visa application surcharge. Now, this one is really clever because it only applies to people you're going to hire for more than 3 years. So if we want to get somebody in here for a very short time and not make us lots of tax and not actually help the economy, you don't get charged anything extra. But if you want to bring them for more than 3 years, you pay a surcharge of 1,400 pounds per person. So that's another 2,800 quid. And then there's something called an NHS surcharge. Now, this is theoretically paid for by the individuals, okay? The individual and their dependents each pay this surcharge. They pay it up front. So there's a 5-year work permit. If I come with a daughter, if I were to come with a wife and a daughter, I would be expected to pay £15,500 up front to the government to allow me to come to this country to pay for the NHS, even though I'm paying taxes. So of course, what happens? The companies pay that money. So because nobody can afford that. Right? So £28,000. So yeah, that is the true, you know, on a piece of back of an envelope, and it's, I mean, that's a very accurate calculation. The back of the envelope calculation is another one I'm about to give you. Yeah, so if you can do anything about that, if you have any access to anyone in government who has any access to, this is the one thing that is going to kill all of that momentum, positivity, success that we are generating. Because we don't have enough people at the moment, you know, now. And actually, with the investment coming in, with the, you know, this announcement about pension funds, hopefully being able to fill some of that post-fund, you know, like the C and D stage funding gaps, you know, we are poised for really strong growth and success. But there is something that actually will, I believe, really is in danger of tripping us up. So, so the other calculation to think about there is, what's that costing us? Okay, so this really is that, and it's me. Okay, you disagree with these numbers. The problem is no one's actually ever done any of this kind of analysis, right? But let's say 1,000 people don't come to the UK because of these issues. And by the way, you know, I think 1,000 is very, very low. But just say 1,000. Average time they'd be here, some people would be here 2 or 3 years, some people would be here for their whole career. So we say 10 years? What's their value? Now, I curated a VP of Engineering and CTO event I did a sort of survey around it. I said, how much is an engineer worth to you? And one of them said, well, I pay them 80,000 pounds, so they're worth 80,000 pounds. Somebody else said, well, I've got a 50 million pound company. I've got 50 engineers. I have no company without my engineers. They're each worth £1 million. So, there's no way of actually assessing how much an engineer is worth to you, but let's say they're worth 400,000, profit margin of 25%, 100 grand, right? So do that calculation, that's £1 billion, 25% corporation tax, 250 million pounds. What taxes are they paying? 10 years times 1,000 people times, let's say, £60,000 average salary today, times half by the time you add up the NI, your national insurance, your tax, the VAT you pay, the stamp duty you pay, let's say half, I have no idea. Somebody could probably tell me. 300 million pounds. 550 million pounds of tax over 10 years based on 1,000 people not coming to this country. If you think 1,000 sounds like a large number, there is a serial semiconductor entrepreneur who's just started a new company, who's opened up in Portugal, and the only reason he's open in Portugal is that. He will hire 10 people in Portugal, absolutely hire 10 people in Portugal this year instead of here. So that's 1% of that number right there, 5.5 million pounds of tax. So I think these numbers are incredibly conservative. Disagree with me, agree with me, but that's the message. That is something that we can all do something about. Right, that is topic number one. And I started with that topic, even though I used my prop, because that's a depressing topic. But the other two topics are very optimistic. So, one, ChipStart was mentioned. ChipStart is an incubator, government funded, that is encouraging semiconductor companies to, basically enter the industry, so a one-year incubator program. Linked to Silicon Catalyst, and I am a Silicon Catalyst angel investor. I'm in the US group. Sean Redmond started ChipStart. A few months ago, I said to him, what are we doing about angel investment around the ChipStart companies and just semiconductor companies in general? And he said, well, nothing. So I said, okay, well, I'll sort of head that up. So do you remember what I said? Tell them what you're going to say. I said it. Tell them what you're going to say. It. So what I'm going to say is, if you know any angel investors, please put them in touch with me. If you are an angel investor, please get in touch with me. And that activity is voluntary from my point of view. It's going to be extremely light touch. And in terms of fees, all angel groups charge fees. We will charge a tiny fee to the companies that raise money, just so that we can pay our administrator and maybe organize an event or something. But we keep it very light touch. But if we introduce our company, say, to Cambridge Angels, and they have a fee, we will waive our fee so long as the total fee doesn't exceed 2%. So, because we're going to charge 2.5%. So really the goal is just to get some cash into these companies. And on Monday is the first online pitch event of 4 ChipStart grads. They're going to do speed pitches on Monday, 20 minutes each, in anticipation of the ChipStart event of London Tech Week, which is in person next Thursday. So, and that is all 12 companies graduating and the 12 new companies being announced. So, and yesterday I organized a practice pitch event so we could test the technology, and I got these companies talking to 2 of my angel contacts who are non-semiconductors. They don't have a semiconductor background, because I wanted the people pitching to understand what people who don't understand semiconductors might be looking for. And I had an email from one of the companies 5 minutes later saying, hey, those 2 guys, and I had to go to a conference, so I wasn't at the end of the call. And he said, hey, those 2 people you introduced us to, they both said they wanted to invest. Can I have their emails, please? So, so these are good quality companies that are coming through. So, so that's that one. And then finally, especially in relation to Newcastle. So I'm the chairman of a charity called UKESF, UK Electronic Skills Foundation. Some of you will have heard of that. So it is the only charity that has what I would call an integrated product in terms of encouraging kids to study electronics from primary school all the way through to post-grad. And what I mean by that is we have a pilot program with ST to get really sort of Lego-type boards into the hands of primary students. We have an electronic sort of Arduino-based program for people in about year 8, year 9 called Turn On to Electronics, a web-based program where they can do some projects and they get further resources. We've penetrated about 20% of all A-level physics classrooms and given training to those teachers and given them something called an electronics everywhere. It's a music mixer. They put it together and it supports 2 elements of the curriculum. It's the only hands-on piece of equipment or electronics that supports the curriculum. That's sort of A-level. Our flagship product is a scholarship scheme that introduces, we have 30 partner universities. This year we had 500 applicants from the best students at these, electronic students at these 30 universities. They get paired up with companies who want to build a skills pipeline. So they either have a summer or a year in industry program, and we put those 2 together. The company gets to interview them and finally choose them. And essentially what that does is it increases your probability of hiring those people massively when they graduate. Yeah, that's sort of and the reason that's our flagship program is it just generates a little bit of revenue for us. Then we have a post-grad, we're talking about a post-grad physics program to get people who've done physics, and lots of people doing physics, not many jobs, so get them into semiconductor manufacturing and process and do a training session there. And what we've just completed, what we're in the process of completing is work with CSA in Wales, a locally focused program that sort of combines all those elements into something that's geared up for that region. So we are going to secondary schools. We're providing them with the boards. We're providing the teachers with training. We're going in doing workshops. We're getting the students to go to universities for one-day programs with professors. And actually, one of the other programs I just failed to mention is Girls into Electronics. Last year, and this year, 400 girls go to our partner universities for a full day of training, lectures. They get an Arduino board. They build a kit. So we've sort of focused that on just Wales and not just women, not just girls, so girls and boys. That is absolutely replicable for the Northeast. And if that needs to be replicable for manufacturing skills rather than design skills, that's absolutely doable. So it's a shame that Guy, I will make contact with Guy, but that needs that's about £100,000 probably to deliver a program that reaches hundreds of students. So I would strongly encourage the Newcastle region to get involved with that. So, in summary, if you're an angel, get in touch with me. And if you know any angels, get in touch with me. Thank you.
Thank you very much. Andy's got a quick question.
Oh yeah, question.
Thanks, Neil. I know some angels.
Yeah.
You sent me the details. My question is...
Getting ahead of myself. Thanks, Neil. Brilliant pitch. I know some angels. You've sent me the details. Are you happy for me to post that on social media? Or...
I should have told you all to do that. Bloody hell, what was I doing? Yeah. No.
I'll do that. Okay, and I'll tag you, and then you'll get some connections. Okay, cool. Roger.
Thanks. Brilliant. Right. One last one, if anyone's got anything. Otherwise, we'll... No, brilliant. Thank you very much. No, sounds very exciting. And next we have Alton Horsford from Nascent Semiconductor.
Sorry, but otherwise people can't hear you on the recording. Just check the switches across. Yes. Everybody deafened by that? So that sees the mark of any academic that you can talk to the guy at the back of the room as though he's your best friend. Right.
Hang on a second, I'll just start from this point.
So, slight change of pace, slight change of tack. So I'm Mark Horsfall. In my spare time, I'm a professor at the University of Durham. My main role in life is Chief Technology Officer at a startup that you've never heard of. So, complete change, and following the advice, I'll tell you something several times, and then I might repeat myself at the end. So I'm going to talk to you about us, and who we are, what we are. Talk about silicon carbide. Sand with coal, and this is how I once described it. We're going to have a little peek under the carpet and tell you all about quantum physics. And once that's scared you to death, we'll tell you about the quantum future, and that might scare you to death even more. Then we can conclude and go off and get a cup of coffee when the time comes. So who are we? Well, we've been in existence for 3 years. We were founded on the 5th of May 2021. Like the royal family, we have 2 birthdays. There's the one according to Company's House, which is when the university founded the company, and then there's the one on the 19th of November, when we actually got our hands on it. We got the keys to the door. We do unconventional, novel electronic devices and systems. So back to my comment earlier, we found a niche that people don't play in, and we can do rather well. I was once told that my biggest competitor was Infineon. Boy, did I laugh. What do? We do device design. So we had a company come to us last week. They want a particular transistor that they can't find anywhere else. Can we help? Yes. We do system design, because we understand how these things work. We can put them into systems, and we can do daft things. We do a lot of quantum. We do bespoke training. If you want to know how we can take you from somebody who does GCSE chemistry to somebody who does PhD level physics in 3 days, bring your checkbook, we'll talk. We also have a strapline. This was invented by our CEO. I can't remember if it was just before or after the pub on the Christmas party, but basically, we don't tell you where you can put it. You tell us where it needs to go. We build solutions that go into fusion reactors, gas turbines, all manner of defence, and stuff that I can't talk about standing here. Silicon carbide, compound semiconductor, was the original semiconductor in 1906. Joseph Round, personal assistant to Marconi, spotted that it glows a funny colour when you put a voltage across it. A little bit of history for the northeast. There's a place just north of Whitley Bay called Marconi Point, where he did the first ship-to-shore radio transmission. You've got to find a very, very large-scale OS map to find that one. It's not even on Google Maps. It's that obscure. Most of us, and the compound semiconductor catapult, will talk about high efficiency, electric vehicles, net zero, all these wonderful things, and how we're all going to have it tomorrow. That's great. Unfortunately, everybody else has wised up to that. Infineon, Wolfspeed, ST, all these big companies. That's not really our bag. People talk about high temperatures because they know you can put this stuff into really nasty places, and its theoretical temperature is about 1,000 degrees. Practically, it's about 500. And that means we can do aerospace. We can build protection devices that will absorb lightning strikes. That's quite a niche market. Something that's this big that will actually survive a lightning strike. Because, of course, we're building plastic planes now, and there's no longer a Faraday cage around the outside of the plane. Now, if you're like me and you hate flying, I really hate flying. Radiation tolerance, or the same bit of chemistry that gives you the high efficiency, the high temperature, also gives you radiation tolerance. And we test our stuff to 10 megarads. That's 100 times higher than Mr. Infineon will sell you with their state-of-the-art high resilience, high radiation stuff. And once we've done that, we can reset that radiation damage and go again. That got us a lot of attention from the UKAEA people who go, oh, can you put these in a fusion reactor? Yes, but not this week. But yes, that's what they want to do. They want to put this in the maintenance robots just outside the tungsten wall in a fusion reactor. It's 600 degrees and the radiation dose is phenomenal, and it's got to last for 30 years. How do you test that? And then, finally at the bottom, the brave new dawn, quantum technology. This is the only way you can put semiconductors and quantum together to make an integrated hybrid conventional quantum system, and we can open the door. Quantum comms, quantum computation, quantum sensing, all in one chip. There's no other material system out there that will allow you to do that. So, how, you ask me? Well, this is how. So, silicon carbide is a stoichiometric alloy of silicon and carbon. So, imagine you're playing with your little Lego bricks as a kid. And it looks like the stuff on the top left. Now, obviously, silicon's blue and carbon's red. All right, so when I draw electrons and holes when I teach. And the top left corner, you see a silicon vacancy. There's a blue ball missing. And that shows up as a defect down here. And this is... No, remember. Yeah, it's all right. Point the other one. Press that one. Point over here. Right. So about here, got really dodgy shakes this morning. There's an energy difference in our defect between if we populate it and if we don't populate it. So we've got missing atoms like vacancies. There's also carbon vacancies. We get extra atoms stuck in. Somebody was talking to us earlier about, where does the carbon go in silicon carbide when you oxidize it? This is where it goes. It becomes a carbon interstitial and it wrecks your MOSFETs. This is why silicon carbide MOSFETs are not as good as they should be. And they've got all kinds of problems like threshold voltage instability. Carbon interstitials. Some good work came out of Japan a few years ago on this. We also end up with a situation of point versus extended defect. So you've got VC VSI and CSI VC. Okay, so you've got carbon silicon divergency and a silicon carbon site with a carbon vacancy next to it. So there's a whole zoo of these dratted things, and I spent 20 years of my life working in semiconductors trying to get rid of them. You put them in accidentally by doing ion implantation, contact annealing, and they'd be a pain. Now I've realised that I've been doing it wrong, and I should have been embracing these little darlings and doing fun things with them. So this is the quantum bit. Down at the bottom, you've got two energy levels, and it's a spin half and spin 3/2 energy level. And they're separated by a small energy that's resonant with an RF signal at 70 megahertz. We can shine a laser on this, so 785 nanometer laser, infrared, not much fun in the university because health and safety people really don't like you. And we pump all the carriers up to the top, so we put our defect into excited state marked by ES, and then it relaxes back. It's an unstable dynamic equilibrium. And there's two options. If you're in a spin 3/2, it drops back to the spin 3/2 ground state, the big red arrow, and that's the dominant transition. That gives out light. This is a photoluminescence type measurement. If you're in the spin half, chances are it drops this metastable state and drops back out at the bottom. This is a dark transition. We can't see it. We've got no idea that it's there. We know it's there. Physics tells us it's there, but we can't actually see this. It's called the dark defect. And so if we're doing this for real in an experiment, well, those are our two dominant transitions. In order to measure it, we want to populate the spin 3/2 state, so we apply this RF signal at the bottom. And what we do is we sweep the RF field, and when we get to the point where RF equals 70, we see a nice big spike in our resonance. Ta-da, that's quantum. What does it look like in real life? Well, here's our PL signal. There's a reason why it's 1.35 gigahertz for people who know me. And you see a very sharp transition. This one's upside down, so it's an absorption measurement. And you can split it with magnetic field. So that's Zeeman splitting for those of us who had to suffer this at level 2 undergraduate in physics. What does that mean? Well, we've got a very narrow line width. And actually, if we optimize that, it's about 10 hertz wide at a gigahertz. It's a very, very sharp transition because it's quantum. You're moving from one quantum state to another. What does that mean? Well, precision timing. We've now got a system where we've got a line that's very, very tightly defined. Very little uncertainty, no jitter. On the other side, we've got magnetic field dependence. We've got a magnetometer. The clever thing about magnetometers on this is because silicon carbide is hexagonal close-packed lattice, that direction and that direction are not the same. And so actually with one pair of defects, I can look at that direction and that direction at the same time. I've got a perfectly orthogonal magnetometer with one sub-micron feature size. All on the same system. Well, the clever thing really is we go away and build one. And this is a schematic, an optically detected magnetic resonance system. We call it ODMR because we can't spell. What does it look like? And I'm going to struggle with the little pointy thing now, so please bear with. There we go. So let's start with the laser, a little bit of beam steering. It goes through a dichroic mirror, large objective lens, onto our sample, which has got an RF signal across the top. We then collect as much light as we can through our high numerical objective lens. It's reflected back off here, and we send it into a single photon counting module. This system is about year big. It's half an optical bench, weighs half a ton, and it's not exactly portable. The great thing about quantum is we need to get it out the lab. I once sat on a meeting with EPSRC, And one of the things they talked about is what we're going to do in the future. I said, we need to get quantum down to that. And all I got from people saying, you can't say iPhone because it's trademarked. Yeah, right. Point still there. When you can put it in your pocket, it works. That phone has more computing power than the US national government had when I did my PhD. What do I use it for? Checking Wednesday's football scores, reading the news and watching Piano Playing Cats on YouTube. What a waste. If we want to do something with this, and I want to set quantum free, we let the engineers in. And we look at that and say, yeah, okay, you can do it optically, it's beautiful, it's wonderful, it does all this stuff, but you can detect that electrically because you detect the electrical transitions and you can do this. And you can actually get a current out of it. Oh, hang on, we've got a current, so we can put an amplifier on it. And as soon as we do that, we don't need all this ancillary stuff. Try that again. No, go the other way. All this, I'm used to working in the university where I can actually reach and point at the board, in case you're wondering. You don't need all this ancillary stuff up here. All I need now is a laser fastened into an objective. I could do this with a fibre optic laser, and actually I put an amplifier across the back of this. I can build that RF generator on chip. I can build that amplifier on chip. I can't do the laser. Silicon carbide doesn't do very well with optics. But everything else you see on there will fit on one 3mm square piece of silicon carbide. I've got a magnetometer in my head that will fit in your iPhone. You can't do this in any other material system. What does this let us do? Well, once we get hold of this, we can build a magnetometer. Well, just kind of showing you that. A little hand wavy, but it's there. And we can do picotesla per square root hertz. And the main interest in this at the moment is anomaly detection. If you don't read the right type of novels, this means detecting other people's submarines where we don't want them to be. That's basically an anomaly. We can do single photon generation. Okay, so if you want to go out and do comm systems and things like that, this technique will also produce a single photon system. So do other systems. This is not particularly unique to us. Position, navigation and timing, atomic clock. We can build a fully ruggedized atomic clock that you can drop, bounce, throw around. I watch Paul laughing now. And it will still work. You can't do that with standard quantum technology. It's very fragile. Our stuff, yeah, not a problem. Especially pure microwave sources, building masers, and there's a lot of interest in that for things like battlefield secure comms. You've got a very spectrally pure microwave source that you can tune electrically. There's a lot of interest. Where does that bring in us? So a couple of moments just advertising us, because frankly, we're wonderful. We're doing magnetometry, we're doing a lot of work in position for GNSS denied environments. There's a lot of money at the moment with the UK government. Sovereign supply chain, what happens if GNSS is turned off? I had to explain this to my son on the way home last night. The trains stop. Well, okay, I came up on Northern, that's not a major threat. Navigation, and it's not about Uber, and it's not about Domino's, this is about everything else. Bank transfers, national grid synchronization, they all work on atomic clocks. And in case you're wondering about the railways, it's the signalling. And one of the comments from somebody is, if you work in distributed sensing, the person who knows the time wins. Timing, comms, training. Oh, the bottom one. Just to go back to some of the things that have been out there. We want to go to the moon. There's a few people I'd like to send one way, but we're off to the moon. What's the time on the moon? It's a facetious question. I can see Sandy Toksvig now with her thumb on the button in QI. I go, what's the time on the moon? If we want to do autonomous landers, the Chinese have just landed on the dark side. It's a fantastic result. We need to do autonomous mining, autonomous landing. We need power networks. We need Uber. Again, you know, how are we going to get around to the moon without Uber? We can't do this unless we have a timing system that gives us navigation, that gives us position. We've got a fully ruggedized, landable, not necessarily by everybody, landable system that you can put on the surface of the moon. It's also small and low power that you can fly it over the top of the moon. But we'll come back to skills. We're working with Durham, which is my part-time job, to produce targeted training for engineers looking to develop quantum in real world. So we have over the years developed training for people in semiconductors. We can start with GCSE chemistry and take you to PhD, 3 days. We're now taking this out, we're going to teach engineers about quantum. Why does it matter? What does it matter? What will it do for you? And our first product on this will basically be quantum for managers. Why does it matter to your company? What should you know about this? When the engineers use the word, what do they mean? We're taking bookings. Obviously, a little bit of the sales pitch there. So where are we? Well, the integration of quantum with wide bandgap semiconductors is a unique opportunity. There's no other material system out there that can do this. I've been looking to do this for a long number of years, checking the audience. When I worked for my previous university, I tried to get this off the floor and it didn't work. So the technological maturity of silicon carbide is really quite good. It's not silicon, thank God, but you can buy wafers, you can do processing, and now we can integrate the clever stuff with it and we can still put it through a foundry. We can go to a foundry in the UK and get them to manufacture quantum parts. Miniaturized ruggedized systems are being developed that will do everything we can imagine. And I'd like to finish by thanking the giants upon whose shoulders I stand, some of which are at the back, and some of which thankfully are not. And with that, thank you very much.
That's fantastic. Any questions, quick questions for Alton at all?
Yes, Andy.
Great, thank you. Sounds like a panacea for lots of ills. I was going to ask, how does your PNT vision or performance compare? UK government trialled a PNT, quantum PNT atomic clock recently. I think it was BAE Systems. Henry White, is, I seem to remember as a contact name. How does your PNT performance compare? What advantages might it have with that system?
Can we get back to you in about 3-4 months when we've got that data that I can stand here and show you? It's smaller, it's lightweight, and it's rugged. I don't say it's droppable because I'm watching Paul's expression. So our chief engineer's in the audience, and I'm just watching his expression. If I say it's droppable, I suspect there'll be words on the train going home. It's more rugged than a lot of others. It doesn't have the same failure modes that you see in certainly the very small cells. They've got certain failure modes that people are concerned about. Ours don't do that. May well have others. But that's the thing, it's a more ruggedized solution than is out there. There's also a question of how good is good enough. That's one for outside.
Brilliant. There we are. Anyone else? No, right. If you could quantumize all of this, that'd be fantastic as well. But,
Yes, but it wouldn't work.
brilliant, thank you very much. We'll move on to Michael Stokely from Oxford Instruments. I think we were having a chat during lunch that, of course, it's all well and good, everyone coming up with really great ideas about what to do in the lab, but unless you've got the right instruments behind you, it's really difficult to actually achieve or characterize it. So, thank you.
Thank you.
This yours, yes? No. Chris Hodson.
Ready to go? All right. Hello, everyone. First of all, apologies from Michael, who couldn't make it. So instead, you have me, Chris Hodson. I'm head of product management at Oxford Instruments Plasma Technologies. And I'm going to give a talk on the future of semiconductor processing equipment and techniques from, well, at least from an Oxford Instruments perspective. Right. An outline of my talk. I'll give a brief introduction to Oxford Instruments,
for those that are not familiar, and the plasma technology part of Oxford Instruments, where I work. An outline of the main application drivers that we see, and then a look at the technology requirements that are coming from those application drivers. And then, depending on how much time we've got, we'll cover a few examples as well. So Oxford Instruments Group, there's a number of divisions. As I mentioned, I work in the Plasma Technology division here. Yeah, the Plasma Technology division here. There is also involved in the semiconductor areas, particularly the nanoanalysis division, asylum research, VTech, and I'll talk through some of the products that they have that are relevant for semiconductors. So the Plasma Technology division, as mentioned, is really focused on enabling next generation devices in semiconductors, and I'll go on to talk about those types of devices that our equipment is being used to fabricate in the next few slides. But I'll also talk a little bit about the nanoanalysis division, the types of analytical instruments that are used. So, for example, AFM, electron microscopy, so EDS, EBSD, and Raman spectroscopy and imaging as well. So overall, Oxford Instruments' vision and view is enabling a greener, healthier, and more connected advanced society. So really, semiconductors is a key part of that. Quantum is already mentioned, but really across all these areas, the fabrication equipment that plasma technology is making is being used for. So the global megatrends, these have already been really well outlined earlier on today. They are the consumer, electromobility, and also as well quantum, which we just heard in the previous talk. So all the kind of things that we've talked about, big data, digital twins, they're all things that we are seeing and looking at as part of our roadmaps. One thing to note is really in these application drivers, there's the amount of semiconductor component that is required across all of these applications is really, really increasing, 3 to 4 times the amount of semiconductor components. And particular compound semiconductors, as has been mentioned today, is really enabling that. So the different market areas that our equipment is being used for. So we've talked a bit about silicon carbide, power electronics for electric vehicle power conversion, GaN power, RF for consumer power supplies, and RF applications that have been outlined previously. With all this big data and all the data centers and AI comes a lot of optical communications. So we're seeing a lot of customers working in indium phosphide-based technologies, gallium arsenide, VCSELs. So a lot of activity around that area. As well in gallium arsenide, a lot of sensing, so 3D sensors either for face recognition or in autonomous vehicles, scanning around the vehicle, LiDAR, for example, as different applications. And as outlined very nicely, quantum technology, complex problems, secure communications, all applications that we see. And also, if I've got time, we'll talk a little bit about augmented reality and some of the solutions that we have for that market. So Oxford Instruments Plasma Technology, we're based in Bristol. We're investing in, at the moment, a 5-year investment, £75 million into a new facility, which is located in Avonmouth, just outside of Bristol. And that investment doubles our application laboratory size, so where we're really investing in understanding how our fabrication equipment, so etch and deposition fabrication equipment, how that impacts, how the processes impact devices. That can be quite a challenge for us because We don't make devices, so we rely on partners to get that data, to get that information, to really understand how our processes impact on semiconductor devices. And I'll go on to some of the examples of that in a moment. This is a slide from published by your research, but I think what's striking here with the different material systems, so gallium arsenide, the indium phosphide, the gallium nitride, silicon carbide, and compound semiconductors, is just looking at the roadmap. In the next 10 years, the number of applications that are being enabled by these compound semiconductors is really, really increasing compared to the previous 10, 20, 30 years. And so it really is an exciting time investing in compound semiconductors. And there's a lot of activity here in the UK on compound semiconductors. And also as well, the different, looking at what are the future material systems, diamond, gallium arsenide, gallium oxide, and different material systems for the future. If I was to pick out one kind of major trend in technologies that's coming from all of this, I'd really say that it's probably surfaces and interfaces. This is because as feature sizes shrink, device structures go from planar to vertical, then the surface to volume ratio really increases. So surfaces become much, much more important. And really the drivers that we're seeing from customers is to lower the optical loss, make devices more electrically efficient, lower electrical losses, and the surfaces and interfaces are really crucial. The quality of those surfaces, in terms of low defects, low crystal damage, it becomes very important. The illustration there is particularly in quantum. I often hear this slogan of every photon counts. So really it's reducing optical loss from where we are today to almost no loss as we go forward. So really we are focusing on no damage. So when we etch something, no plasma damage in the first place, or removing damage from surfaces and interfaces. So the different solutions that our equipment and our processes are for. So I mentioned the damage removal, also looking at interface optimization. So etching an interface, cleaning an interface, removing the surface layers, and then putting down a passivation to ensure that we get a high quality of interface. We're also seeing as well demands for ever advanced architecture features. So I mentioned augmented reality. They're looking actually at a slanted etch, but also we see high spec feature etchers really trying to control the etch profile, the features, and then also as these features get ever more complex, trying to deposit and coat in these different feature structures. So I mentioned the four main areas that we're looking into, so the discretes, devices, opto devices, 2D materials is also something that's very important, next generation R&D, and then also quantum technologies. And all of these, the main technologies that fabrication technologies that we are focusing on is atomic scale processing, so atomic layer etch, atomic layer deposition, plasma etch and deposition, and then also ion beam etch and deposition. And what's really important that we're seeing is control, and looking at use of AI and in situ monitoring, combining that with AI to achieve the control of our processes, controlling the plasma at the surface, and really managing the thermal budget with it when we're processing, and all of that increasing productivity, throughput, and yield. So a couple of examples. We've talked a bit about wide bandgap semiconductors, so gallium nitride, silicon carbide. On the left here, we have two different types of gallium nitride devices, normally off devices. So a PGAN hemp structure and a recess gate MIS hemp structure. And here, as I mentioned, the... oops, sorry. Did I put that back into... Thank you. So here, as I mentioned, in this recessed gate structure, we are etching a recessed gate structure of just 20 nanometers. And here, the control of the depth becomes very, very important when it's just a 20 nanometer etch. And as well, when we're doing that etch, we need to make sure that the surface quality, so the surface roughness and the surface quality is as high as possible. And there we are choosing atomic layer etch to get both this control and also to get a very smooth surface. And then once we've done that etch, then using plasma atomic layer deposition to put a passivation layer down. So this is for a kind of an RF type, GaN RF type device, or alternatively also smoothing in a PGAN HEMT. On the right is a process that we have for silicon carbide, and that is an alternative to using CMP and etching the surface with a plasma to effectively polish the surface in a similar way to CMP is doing, but removing the surface damage. And we've characterized that both electrically, making devices with partners, but also using metrology such as Raman spectroscopy, looking at the density, AFM, looking at the surface roughness, and EBSD, looking at the crystallinity of the surface. So combining all these techniques to really understand the surface and how that impacts on the electrical device results. This can be a very time-consuming process, so we're always looking to, to fabricate a device can take several weeks, months even, and is very costly. So we're always looking for short-loop methods, and hence the focus on the metrology to really directly and rapidly characterize the surface so we can try to understand what the impact will be on devices. So I mentioned there the example of the surface smoothing already, and that is where an etch can modify the surface of the device and of the structure, and really where we're using atomic layer etch to get that best quality of interface possible. One area that we have just looked at for quantum is the deposition of superconducting films, so niobium nitride and titanium nitride. One of the limitations that we have here is that conventionally sputtering is used for these materials, but as device structures changes and they become higher aspect ratio structures, then there's the need for a conformal coating, so atomic layer deposition is used instead. But this is slow, so we've introduced a new equipment for depositing these films much quicker in a conformal manner, so 3 times faster than we currently can for quantum. And then I'll finish on an example of the slanted etch that I mentioned. This is for a grating, for optical grating for AR. So that is basically taking the light from the display on the side of an AR headset and then diffracting it into your eyes. And so that grating is an angled grating, which we can do by ion beam etch to achieve that kind of profile. So really different demands in terms of the structures and what it is that we're trying to etch. So a summary there, we see the trends for the future of surfaces becoming much more important, surfaces, interfaces, looking at damage removal, interface optimization, and etching and depositing onto ever more complex features with higher requirements for their fabrication. Okay, thank you.
Time for one quick question before we move on. If everyone's... No? Okay, brilliant. Thank you very much. And with that, we'll now move on to Derek Holiday.
Oh, yeah. Do you want to go
There
on?
we are.
To clip that on to your waistcoat there.
Brilliant, thank you very much. Oops. Just get the pointer working in case it wants to keep doing something.
So just,
Is it going now?
yeah, and there's the highlighter.
Ah, that's brilliant. Fine, thank you very much. Okay, good afternoon. So my talk this afternoon is about driving the electric revolution movement, if you like, in our industrialisation centre in the northeast, and how hopefully it can help the semiconductor industry in the northeast. So my name is Derek Holiday. I'm the centre lead for the northeast Driving the Electric Revolution Industrialisation Centre, abbreviated as or known as a DEREC, coincidentally. I don't know if anyone really knows much about driving the electric revolution, so I'll give a brief introduction to what it is. It's a government intervention, effectively, which was born out of a proposal in the northeast, where it was identified that there was an opportunity around electrification technologies to help companies scale up manufacturing processes to exploit the opportunities offered by electrification. This idea was pitched to government, and government thought it was a great idea, and they provided some money to set up some industrialisation centres and to run some projects. £80 million at that time. It wasn't a huge amount of money, I guess, in the great scale of things, but it was the biggest investment that we'd seen in our area at that particular time. And the technologies that were chosen to be the focus of this are power electronics, electrical machines and drives, PEMD technologies. So these are underpinning electrification technologies. We see PEMD systems, obviously, in things like electric vehicles, and that's a good example of a complete power electronics, electrical machines, and drive system. But these are underpinning technologies which you'll find in a range of applications, from mobile telephones, white goods, through to industrial processes, and so on. And without wanting to sort of labour all of that stuff there, we recognise the importance of these technologies and the opportunities that they offer to us. So this was the mission of Driving the Electric Revolution, DER. It was to work with industry to grow UK PEMD manufacturing capability, capacity and competitive. And as I mentioned earlier on, some of that funding that came from government was used to set up 4 industrialisation centres, the DERECs. And in those centres, the funding that was there was primarily used to provide equipment which was there to fill identified gaps in our supply chain capability. And that was following a really quite extensive consultation with industry. 4 centres were set up. You can see there's quite a lot of dots there on the map. They're kind of clustered. There's one centre is around the northeast, which is obviously the one that I lead. There's one in Scotland, there's one around the Midlands, and there's one in the southwest in Wales. And they all have different specialisms. The one in the northeast is around scale-up manufacture of power electronics and electrical machines, power electronics and drives and electrical machines. In Scotland, I previously worked at Strathclyde, it's based around Strathclyde University. It's set up around high power systems. They have a lot of track record in megawatt scale equipment and systems. The Midlands, well, they do a lot of stuff, obviously, around about WMG, Nottingham. They are very much component level stuff, developing machines, developing devices and power converters that use those devices. And then the Southwest in Wales, based around the Compound Semiconductor Applications Catapult, that's very much based around materials. So there, obviously, people involved in this industry will know in a great deal of detail exactly what goes on at CSAC. They're developing devices and manufacturing process, but they do it at quite small scale. And supporting that activity as well, if you go to places like Birmingham, they are into magnetic materials and recycling magnetic materials, and then around about Bristol, they do additive manufacturing and so on. So on the right-hand side there, we can see the network partners. The institutions highlighted in red are the centre leads for those four centres. And then you can see in the northeast, Scotland, southwest, and Wales, and the Midlands, those are all the partners. So it's quite an extensive network of people that we are able to call upon. And it gives access to several hundreds of millions of pounds worth of capability over and above what was invested in through the DARE programme. So this is just a little bit of detail about how some of that money was spent. I think maybe the one to focus on, because we're in the northeast, is probably our centre, but you can see there how the equipment was actually spent and where it was actually located. Importantly, the equipment was carefully chosen and located where there was capability to actually use it. Okay, that was how it ended up where it ended up. So in the northeast, we've largely got a power electronics packaging capability. And following that packaging capability, we're then able to take those packaged devices and integrate those into drive systems. We have packaging equipment, which is industrial scale for packaging and also for surface mount PCB manufacture. And again, if anyone's interested in how we use those devices, for example, to drive electrical machines, we've also got capability to prototype and assemble and manufacture electrical machines as well. So the total investment to date has been around about £45 million. The equipment that we've got at our centre totals about £10.5 million. There was an initial tranche of funding, and we've just gone through the commissioning stage, and now we're starting to use that properly in anger. Importantly, I think, I'm also currently in a procurement phase. I have some additional funding, and I'm looking to spend that wisely. What I am here to do is to support industry, not just nationally, but also clearly in the northeast. We're in the northeast. So it's great to build that relationship with the power electronics community and do as much as we can to support the industry and power electronics community in the northeast. I need to make sure that the centre that I lead is as useful to as many people as possible. So because I'm in procurement mode, if people have particular needs for manufacturing process development or capacity, I'm all ears. Let me know, and I'm happy to consider any suggestions as to how best to spend the money. If we look very broadly, it's a very simplistic diagram perhaps of a PEMD value chain. So again, probably the more important one of them is the one on the bottom, which is more focused on power electronics. That's how we within DER have defined a very simple value chain. If you look at what we have at our centre, okay, so I'll just look at our focus on our centre now. So we're located opposite the Nissan plant in the old SASME building. We might be moving from there at some point. We're working on that at the moment. It might not be the best location for us currently where we are, but we're considering various options. But our current location is at the SASME building. And what we have there is open access equipment and staff who can actually use it. We have capability to use that. I think, and you can see our team there, it's a modest-sized team at the moment. We're currently recruiting. I'm sure that those of you who are also trying to recruit will know how challenging that actually is, but we've currently got a couple of new senior engineers coming on board, and we are also looking to recruit more people, particularly for our power electronics side. But don't consider this as being DER in the northeast. Okay, we're able to call upon all of our partner institutions, for example, Durham University is part of the DARE network in the Northeast. Newcastle University is as well. A whole bunch of institutions. We are partnered with people like OREC and so on. There's a whole bunch of capability that we can call upon. And if we can't find that capability in the Northeast Centre, we're also a national network. The 4 centres work together very effectively. So we're able to piece together, if we don't have the capability, we're able to piece together with the other parts of the community a complete capability across the network. So it's a modest-sized team as we can see it there, but we're able to call upon much more expertise as and when we require it. Our 2 main capabilities that we have at the moment, which is about £10.5 million worth of investment, is in a power electronics packaging and electrical drive assembly and scale-up capability, and also an electrical machines capability. Just to give a brief idea of where we are with our centre at the moment. So each of these boxes there represents a bit of equipment that we've got. It's generally industrial standard equipment. It's designed, if you like, to follow on from where the CSA could take you to in a device development. They're geared up to do just a few samples. Our equipment's specified to sort of go into the hundreds of thousands of samples, if indeed that's what we need. So it's proper industrial manufacturing equipment. And so these are the various different bits of kit that we've got and the various processes that we can play with if we're trying to help someone develop a manufacturing process. But I think also the important thing to remember is that this stuff all fits together to give an end-to-end capability. So the stuff that we have got at our centre is very much at the back end of processing. So we can't do wet processing of silicon, but if we're able to get hold of silicon chips, we can then package those and process those. We do have wet processing capability if we then go back to our main campus and work with colleagues within our building on main campus. So we do have capability to do that more end-to-end work piece as well, if that's what's required. We've got some really nice diagnostic measurement equipment as well for examining our processes and confirming that we've done everything correctly. Currently, we've got X-ray and CT scan, nice digital microscope. We've got pull and shear testing. I'm also looking to bring on some more equipment later on, but I'll talk about that in one of the later slides. Again, without wanting to labour it, we've got exactly the same thing from our electrical machines side for anyone who's interested. Perhaps what's important here is that if you look down in the bottom right-hand side there, you can see we've got environmental testing. We've heard a bit this morning about testing, proving devices out. So we've got some very nice environmental testing equipment for devices or boards that people might want to make, a full range of equipment there. And we're also bringing on board a power testing, power cycling capability as well. And that should be arriving within the next few months. So thinking about all of that, I guess comparing with the previous version of this slide, a couple of bits have dropped out because you can't clearly do everything. But if you look at the bottom bit, which is based on our semiconductor capability, we think we've got a pretty good coverage across the board of requirements there in terms of making a device and testing it and getting it working. Here's just some nice flashy pictures to give an impression of the kind of kit that we've got. And if anyone wants to come and visit us, please do. We're very keen to develop industrial contacts further and to help you, for you to come and see what we've got and to find out how we can help you, and also for you to tell us what it is that you would need from a centre like ours. So this is really just focusing this one. Forget the bit on the right, that's a dyno for motor testing. The bit on the left is perhaps a bit more important. It highlights some of our testing capability for environmental testing. Here's our clean room capability as it currently stands. It's a class 8 clean room, so good enough for packaging, prototyping, and then making PCB. So on the left-hand side there, you can see we've got a sinter machine and a washer next to that. So we're working with a local company developing a sintering process. We've got a Corda 7 X-ray machine on the right-hand side there, very good for assessing the quality of the things that you're making, quality of your bonds and so on. I'm also looking to bring on board a CSAM capability as well, which will be really nice and complete our sintering capability. Not so easy to see, I guess, from the left-hand slide, but that's effectively a full SMT line. So we've got, we can lay down solder paste, we've got optical inspection, we've got component pick and place, we've got a full reflow oven with optical inspection again at the end. And we've also just invested in a vapor phase oven as well, so we can do faster prototyping. For those of you interested in automating various bits and pieces, we've also got some expertise in robotics, and that's something that we're developing much more as an activity as well. That seems to be quite popular, particularly among smaller companies. And then here's just a kind of a taster of the shopping list that I've currently got. So high power supplies for testing components and devices. Scanning acoustic microscope is very useful. Power electronics thermal cycling test bench, again very useful for proving out devices. For want of a better name, an abuse chamber, so people who want to do longer term tests of devices, components, or the systems that you make with them, with all sorts of monitoring and data logging and so on. That's a capability that's coming on board. We heard a lot this morning about thermal management. We have really good thermal management expertise in our university, some very clever ideas of cooling devices, cooling systems, and so on. And one of the big investments that I'm making at the centre is around that whole area. Laser cutting and laser welding, quantum vacuum impregnation, etc., etc. I'm in procurement mode. If you have ideas about things that you think would be useful to the power electronics community in the Northeast, please let me know. I want to make sure that we are as useful to as many people as possible. So, in summary, we are sector agnostic. I know we were set up to do power electronics, machines and drives, but as far as I'm concerned, as long as whatever we're trying to make can be accommodated in our machines, or we can adapt our machines to accommodate it, I'm happy to look at any market. And I know there's a lot of activity in the Northeast around RF work and space applications and comms and so on. Not power electronics, but I'm all ears if you think we can be useful to you. We were originally set up for higher TRL, but again, I saw this morning some of the talks, a lot of much more fundamental, lower level research going on. We're more than happy to accommodate that as well. Work with us. Equipment is it's open access. That's our business model. So it's there for people to use. Doesn't mean it's free. Okay, but we have a whole range of engagement models. We can do CR&D type projects. We can do direct funded consultancy type projects. We can collaborate on research, EPSRC, responsive mode, all that kind of stuff. We're open to any kind of operating model and so on. And then finally, we can support product development and prototyping, process development, analysis, etc., etc., etc. If you think we can help, please come and talk to us. Thank you very much.
Thank you very much. One quick question, perhaps? No? Right.
That's good. I overran. I apologise.
No, there we are. Yeah,
Got a bit
we're
of
slightly
time
behind, but we'll make it up before the end. And we'll hand over now to Rob.
Yeah.
Right. So a couple of things to start off with. One, there's a typo on the programme. I've got myself, well, it's been put down as Dr. Opfar. I'm not. My presentation will clearly show that. And the second one, yes, I am a Yorkshireman. I was born in Yorkshire, bred in Yorkshire, and now work in Yorkshire. But I think the Northeast is where I found my feet in clean rooms, and want to go through what we're doing at Leeds University to try and inspire this next generation of clean room engineers, be they technicians, equipment engineers, process engineers, development engineers, and so on. So there's a bit of a jigsaw to put together here. What are the skills that a good engineer needs? How do we get those in place? How do we align them? Now, my PowerPoint skills aren't good enough. Depending on what the application is, be it production, development, some of these pieces are going to be bigger and smaller. But like I said before, I started in the Northeast. I was a Durham graduate back in the early 90s, working in a clean room, and that to me is where, that's probably the biggest influence on my career in semiconductors, that early chance opportunity to go and work in a clean room. If there are any clean room suit manufacturers here, please just start making them a bit bigger. You've been shrinking them over the years. They're getting a little bit tighter now, so it must be something to do with Moore's law that they're getting smaller. I then went to Fujitsu down in Newton Aycliffe, just outside Darlington, as a graduate engineer. So many wonderful opportunities there. Yield improvement, how a process can affect a device, how to control a process, how to control equipment, that whole statistical process control. And then a lot on tool commissioning. I have worked in clean rooms where they believe you take a product from the manufacturer's case, plug it in, put a bit of gas to it, press on and it'll work straight away. But that whole tool commissioning and new product introduction into the clean room. Downside of that, Fujitsu, wonderful control, wonderful opportunities, but very little chance to actually develop a process. So we were very much maintenance there. I went back to Durham, had this wonderful chance, device design, process development, and then a big thing for university clean rooms back then, how to fix bloody equipment, okay? How to, on a Monday morning, get it back to the state it was in on a Friday afternoon. I see a few of the current Durham students laughing at that. I'm glad to see it hasn't changed that much. I then left partway through my PhD. At that point, Siemens was opening up on Tyneside. I got a very nice offer to go spend a year in Munich, working for the Centre for Process Support. It was a worldwide Centre for Process Support. And the big learning from that was, alongside all the wonderful things they did, design of experiments, the chance to develop processes, work with equipment vendors on beta sites in terms of hardware and new chemistries and things like that. It was that influence of these people who'd been in the industry for 20, 30, 40 years and just knew everything, knew everybody and things like that. And then went back to Tyneside for a short time before the inevitable being called into the canteen and told that the factory was closing. But in those months I was there, that was really good for troubleshooting, how to integrate, how to problem solve a line that takes 3 months to make a single device. I then went down to Gmail in Caswell. Apologies if there's anybody here from Gmail in Caswell. No, good. What an experience. Oh my God, how not to run a clean room. And it was the complete and utter other end of the scale compared to what I'd seen at Fujitsu and Siemens. Don't ever have a clean room with a wooden floor that's got woodworm in it. If you are going to buy a deposition kit, you'd also need to buy the metrology to make sure what you're putting down is actually silicon dioxide rather than something else. My time there, I decided to limit for my own sanity. I then went down to South Wales and worked for STS, now KLA or SPTS or whatever other name you want to give them. This was all a bit of a while ago. And it was that bit to start to look at, you know, there is a spec, it is a customer focus that you need on all of these things. Whatever fab you're in, there is an end point that you're trying to get to, and a bit of exposure to non-silicon based processing. Then, place that I stayed the longest, Hazel Grove, was then Philips. It's had various names since then, and I worked across process development, device design, picked up loads of, or refined skills there more than picked up new skills. So process integration, still fighting it today. Just because the lithography is perfect, just because the etch is perfect, doesn't mean when you put the lithography and the etch together it's going to be perfect. That knock-on of one effect onto the other. Lots on tool commissioning and new technology introduction. So we brought in a half-micron stepper there while we were there. And then a lot on project management and commercialization. I remember being called into the development director's office so many times by saying, is it good enough? And I'd be like, well, yes, it is, but it'd be really nice to do this, this, and this. And he'd be like, get out, you know. If it's good enough, we're going to sell it, okay? So there was all these skills there. I then took voluntary redundancy. I worked myself all the way up to development manager for Philips and spent all my time in meetings, doing costings, looking at projects, never going in the clean room unless it was to escape a meeting. And so I decided to come back from the management side. I set up my own consultancy business. I went around lots of different universities helping them either find foundries, working with them on building their own clean rooms and things like that. So that was really much, it really showed this need for skilled clean room engineers. Yes, you can be the best designer. You know, the amount of discussions I'd have with people, they wanted 50 nanometers of oxide at the bottom of a 10 micron trench. Well, you've got to put it everywhere to get it there, and oh, we'll just remove it off the sidewalls, and all these wonderful things. That whole experience of being in a fab was there. So then I took a break from clean rooms, wanted a family, didn't want to be chasing round all the clean rooms around Europe and in the UK, so I went into education. I was working with Hitachi, and they donated a scanning electron microscope to a school that I was at, and the kids found it absolutely fascinating. That's a flea up there. It looks a bit skew-whiff because I'm of the era that if you wanted to take a picture on an SEM, originally you used to have to use a Polaroid camera. None of these digital frame grabbers or anything like that is far too easy these days. Having to open the shutter for about 12 seconds and not move while it was open, or it messed up your image. That's about 6 put together. But it started to really crystallise for me that it's such a fascinating industry, and if we can get school children, students into clean rooms, they're going to absolutely love it, okay? So, after that, saw that Leeds had built a new clean room, and 18 months ago, 19 months ago, I decided to come back into clean rooms. I just couldn't get it out of my system. It's the thing I'm passionate about. It's the thing I really enjoy. So one of the students put this together for me. I apologise. They have a terrible taste in music. If there is sound, it might be better turning it off. I told you. Okay. We're based in the Sir William Henry Bragg building. It's a brand new materials building at Leeds. We have a 800 square metre class 10. I'm old school, class 10, none of these ISO rubbish. Clean room. We are full of the internal Leeds people, PhDs, researchers doing work there. We have lots of SMEs come in and use the facility. And the big thing that I'm involved in is the training. We do so many different levels of training, from individual equipment to 4 or 5 day courses. We're supporting production across the country, really. So short loop runs, full device runs. We do process development. We're helping a few companies out that are building their own facilities but haven't quite got as far down the track as they come. So the bloody motorcyclist turns up on a Tuesday morning, can you get these done by 3 o'clock, and they take them back and get it finished. The thing that impressed me with Leeds is that it's a miniature industrial clean room. It's been built really, really well, put together. Everything that you'd find in an industrial clean room is there in Leeds clean room. That's almost like a time that to perfection, wasn't it? Which is not how it usually goes. Oh no, don't start again. Right, so we opened in January 2022, going really quickly. About a £10 million clean room. We've got about £8.5 million of equipment in there. Oxford Instruments, where's he gone? Yeah, we've just bought £2.5 million worth of etchers off them that we're just installing at the minute. So we're still evolving as our technology base. So we're trying to inspire this next generation of engineers or clean room people, be they design or process. So this is Roundhay School. They came in a few months back. We did a miniature school logo. There we go. Inside the Zero of 1903, we put another logo. They did the resist, spin, the bake, the exposure, looked at it under my scope and absolutely Loved it. What more does a teenager want to do? Put a housefly in an SEM, look at its eyes and things like that. But again, it captivates them, it pulls them into wanting to come into the area. I was told that under no circumstances could you have any under 16-year-olds in clean rooms because it's too dangerous. So I arranged some 15-year-olds to come in to do a week's work experience. So we took them on the Monday morning, all the relevant health and safety, obviously, and everything like that. And then by the end of the week, they had a fully packaged, fully working device. And I think their comments sort of speak for themselves. Hope to pursue this field at the university level. Can't believe the level of precision. But 3 of them came in. One of them, yeah, I don't think he's going to be a clean room person, but 2 of them absolutely set on it now. Still in touch with them every now and again about what they're doing, what they're wanting to do at A level and so on. So there's absolutely nothing to stop bringing in, you know, the younger generation into clean rooms and getting them hooked from quite an early age. At the other end of the scale, we run a yearly national training course. It's an intensive week. It's built up of practical skills in the clean room, followed by, say, a lecture on lithography. We pull in equipment vendors and suppliers to do the bit on that technology. We're in partnership with CISM down in South Wales, so Swansea and then Cambridge as well. They send people up. And it's just very briefly, we'll need sound on this. Anybody lip read?
This course is going to provide plenty of benefits for me. So skills like working in a clean room and all the equipment and processes that I've used today are processes that are used in industry now.
So here you can really learn the real background, how the things work and how the materials are being fabricated and what are the challenges.
So, going as quickly as I could, said I would. This is what I see as how we're going to pull people in and what they need to know. So the first is that opportunity. They need experience of clean rooms. We need to we've got some projects coming up with a company in a school in the northeast in Middlesbrough. We're looking for somebody with industrial possible links to help with that. We've got the sixth form coming down to start on a little project in the clean room, so that should hopefully another set of engineers coming through. You need the basics. Clean rooms are hideous places. They use hideous chemicals, hideous gases, high voltages, everything else, so you need that health and safety. You need to know how to use the equipment, but then also how to control it. Still, that ongoing battle, just because it did it on a Wednesday doesn't mean it does it on the following Wednesday. You can never have too many measurements. If you're in a clean room, measure everything you can and see how that goes on and affects the device when it's finished. I still see there's a big gap there where people think you can improve a device by just design. There's also that side of it where you're going to improve it by improving the process. Experimental design of experiments. Statistically running 8 runs instead of whatever it works out at, 32 or 64 runs. Massively underused tool, and that's something that can optimize processes really well and therefore optimize devices. Process integration, like I've said before, just because one process works and the other one does, put the 2 together and a whole new set of problems to solve. And then never stop learning. You know, I look back on that picture in '91 from the first clean room I went in and just think, oh my God, you know, a manual plasma etcher with 2 big dials as a match unit and sending voltages to MFCs, and I look at the latest etchers that have come in and the control of that. There's always going to be something new to learn. I did have another video, but I'm going to cut it if you need the time. Or edit in afterwards. It's really good. It's what one of the undergraduates did. But that's it. Thank you.
So, well, brilliant. Yes. No, I think I remember being dragged off when I was about 5 on a day out to Essex University when they still did science, and seeing a fly under an SEM. And I've always loved FCMs ever since, so it does have an effect at the end.
It does, yeah.
And I also remember recently going back to the old sixth form and saying, right, here is a talk about going to university, why do you want to go? And quite a lot of people just go, because I've been told to. And so giving them like an actual aim to go and do is fantastic. In the interest of, any questions for Rob at all? Or?
That's what I like.
Champion. So in the interest of time, if the Durham contingent is Amelia is definitely not on no. So we've got a gap at at 4 o'clock, so we can have a break now, grab a cup of tea, and then we can start with Steve on time again, if that's all right. Where's Steve gone? There we are. Yeah, is that all right? Or?
That's fine, yeah.
Brilliant. Yeah, there we are. So, right, we'll see you back on time at 4 o'clock.